The sun will kill everything. You've been told Earth is safe for 5 billion years. It's not. The sun won't wait for its big red finale. Oceans, ozone, and even plants fail on quieter, earlier clocks. The killer move is a slow brightening you can't see. Most people think red giant equals the end, but the real shutdown starts while the sun still looks normal. In the next minutes, I'll map the sun's final 100 million years and the thresholds that flip Earth from lush to lethal: moist greenhouse, carbon drought, ocean loss, subgiant switch, red giant. I'll also show the one engineering trick that might buy time and the irreversible moment it can't undo. How the sun actually works. The part most people miss. The thing most people miss is simple. Stars brighten as they age, and that slow creep wrecks climates long before anything dramatic. Most people picture a swollen red sun. The real danger is same-size sun, more watts. The sun's luminosity ticks up roughly 1% every 100 to 110 million years. That sounds tiny. It isn't. Earth's energy balance is a razor. Add a couple watts per square meter and feedbacks do the rest. Quick question: if a 1% nudge can move ice sheets, what happens when you stack that nudge for 100 million years? Here's why that matters to you. If you plan around 5 billion years until red giant, you miss earlier failure modes. Oceans don't vanish because the star explodes. They leak because the thermostat slips. As brightness rises, weathering drags down CO2, plants struggle, humidity climbs, and the upper atmosphere stops being dry. UV splits water, hydrogen escapes, and the oceans quietly drain. Curiosity gap: which falls first, water security or the carbon supply? What's happening inside the sun? In the core, hydrogen fuses into helium via the proton-proton chain. Fusion pushes outward, gravity pushes inward. Over time, helium ash accumulates, the core contracts and warms, and fusion speeds up slightly. To keep balance, the outer layers radiate a bit more energy. That's the main sequence brightening. No drama, just a slow dial turn. Most people think bigger sun makes us hotter. The real killer is same silhouette, higher output. Let me give you a clean mental model. 3 dials: pressure, temperature, opacity. Gravity sets pressure, pressure and temperature set fusion rates, and opacity dictates how easily energy leaks out. As helium piles up, the core heats, fusion ticks faster, luminosity rises. Earth's climate is sensitive to the difference between energy in and energy out. A small mismatch triggers feedbacks. Water vapor rises, ice retreats, albedo drops, and the system locks into a hotter equilibrium. Here's the part nobody tells you. The thermostat isn't a knob, it's a ratchet. Once it clicks forward, backing up gets hard. Curiosity gap: what fails first in that ratchet? Stratospheric dryness or plant metabolism? Quick stakes check. Early on, Earth's rock thermostat fights for us. Silicate weathering pulls CO2 from the air faster when it's warm and wet, cooling the planet. But helpful becomes harmful. Push hard enough and CO2 drops toward plant limits while humidity keeps heat in. 2 different locks start picking themselves. The moist greenhouse opens a hydrogen leak upstairs. The carbon cycle starves photosynthesis downstairs. Which threshold trips first in most models? Hold that thought, I'll show you. Now, how do tiny changes melt climates? Simple. Energy in minus energy out equals energy stored. Increase incoming by a few watts per square meter and you bank vast heat in the oceans. Water vapor scales with temperature, about 7% per degree, so warm air grabs more moisture, which traps more heat, which makes more moisture. Clouds matter, but when the upper air gets wetter, the cold trap that kept water out of the stratosphere weakens. UV splits water, hydrogen leaves. That's a one-way valve. Aha moment. The end of oceans doesn't start at the shore, it starts above the clouds. You might be thinking, can plants just fix it? The tricky part: the planet's thermostat is rock-driven, not forest-driven. As temperatures rise, weathering accelerates and CO2 falls. See 3 plants weaken as ambient CO2 nears their compensation point under heat stress. See 4 plants hang on longer, but not forever. Biology helps until it can't. Pattern interrupt. The planet cools itself by deleting plant food. Here's the vocabulary we need for the road ahead. Main sequence: long, steady core hydrogen fusion with quiet brightening. Subgiant: core hydrogen runs out, a hydrogen-burning shell ignites, luminosity rises, and the radius starts to swell. Red giant: much larger and more luminous. Shell burning dominates until the helium flash resets the core's thermostat. Later, helium burns relatively steadily on the red clump, then double shell burning on the asymptotic giant branch drives pulsations and significant mass loss. Each stage shifts output, spectrum, and wind, progressively harsher for Earth. Shortcut nobody teaches. It isn't the radius increase that ends habitability first. It's the slow brightening while the sun looks normal. Planets are thermostats only when chemistry can keep up. Eventually, either the upper sky gets wet or plants hit CO2 limits. Once one threshold trips, the other gets easier. If you remember nothing else, remember this: thresholds stack. Curiosity gap: how wet does the stratosphere have to get before hydrogen escape outruns replenishment? Before we move on, timing matters. The brightening is slow, percent per 100 million years, until late main sequence when the pace quickens as core hydrogen runs out. Climate systems hate accelerations. Our first irreversible moment arrives earlier than anyone expects, the day the stratosphere turns wet. Coming up, I'll show you the trigger, the telltale sign, and why rain can't bring that water back. And right after that, we'll answer the question you've been asking. Does carbon starve forests before the sky springs a leak, or does the leak beat the drought? The moist greenhouse, Earth's first death sentence. Here's the mistake most people make. They picture oceans boiling like a pot. That's the runaway greenhouse. The earlier killer is quieter, the moist greenhouse. Pattern interrupt. The oceans don't roar, they whisper away. It starts the day the stratosphere, which should be bone dry, turns wet. Once water vapor routinely reaches high-altitude ultraviolet tiers H2O apart, hydrogen escapes, and that loss is permanent. Curiosity gap: how much water up there is too much? Hold that, because the number is small, and crossing it is the point of no return. Why this matters to you is simple. Do it long enough, and you erase oceans even if the surface still hosts rain and waves. The threshold isn't absurd. A modest uptick in solar flux, reinforced by water vapor feedback, weakens the cold trap, the frigid barrier near the tropopause that usually freezes out moisture. Warmer tropics lift the tropopause, deep convection lofts moisture, and the stratosphere stops being dry. Aha moment! The end of oceans starts above the clouds, not at the shoreline. What's actually happening? As the sun brightens, surface temperature nudges up. Warm air holds more moisture, about 7% more per degree, so the upper troposphere gets wetter. The lapse rate shifts, cloud tops rise, and the boundary that used to block water leaks. Once enough H2O crosses into the stratosphere, photolysis splits it. Hydrogen, being fast and light, reaches escape speeds from the upper atmosphere. Oxygen reacts and sticks around. Hydrogen leaves. That's a one-way valve. Curiosity gap: can clouds save us by reflecting sunlight? Short answer: sometimes they help, but not enough once the cold trap fails. Let me give you the tell. Today, stratospheric water mixing ratios are a few parts per million by volume. In a moist greenhouse regime, models show they can rise by orders of magnitude into the tens to hundreds of ppmv. You won't notice from a beach, you'd see it in spectra. That's the thumbnail moment: satellites showing a wet stratosphere, rain that doesn't return. Pattern interrupt: rain is a round trip, escape is a one-way ticket. Now here's where most people mess up. They think more plants will absorb CO2 and cool the planet. Two problems. First, moist greenhouse is a water story, humidity and photolysis, not mainly CO2. Second, warming accelerates silicate weathering, drawing CO2 down and starving plants. Biology can't scale its way out. Under heat stress, stomata close to conserve water, which further limits CO2 intake. The feedback that used to help stalls right when you need it. Curiosity gap: if plants falter while the sky leaks, which fails first in your lifetime's distant future? The leaves or the cold trap? Energy balance makes the trap clear. Increase absorbed sunlight slightly, long-wave opacity rises as humidity climbs, and the planet must warm to shed the surplus. But that warming fuels more moisture aloft, which raises opacity again. Clouds complicate this, but high, thin anvils often trap more heat than they reflect, and low subtropical clouds can thin as seas warm. The reason this works is relentless compounding. Each degree buys the next degree cheaper. The thermostat ratchets, not slides. Regional dynamics make the leak faster than you degas. The tropics do the heavy lifting, literally. Deep convective towers punch highest there, injecting moist air into levels that used to be safe. With weaker equator-to-pole gradients in a steamy world, polar regions don't bleed enough heat to compensate. Nights cool worse because water vapor throttles infrared escape. Heat waves last longer, each one pushing more vapor into the upper air. Curiosity gap: if nights stop rescuing days, what's left to slow the leak? Common mistakes to avoid. Assuming ozone blocks water photolysis, ozone absorbs UV, but water above the main ozone layer still gets split. Believing rain brings mass back: once hydrogen escapes, that mass is gone forever. Counting on polar night, humidity undermines the radiator effect. Thinking we'd see ocean levels drop early, thermal expansion and ice melt dominate sea level long before space escape shows up in shoreline. Quick win math to feel the timescale. A 1% solar increase adds about 2.4 Wm2 at the top of the atmosphere. After reflection, order 1.2 Wm2 is absorbed. Alone, that's slow. But stack it with suppressed nighttime cooling, potential reductions in low cloud reflectivity and weaker ocean mixing, and excess grows. Meanwhile, every extra degree boosts humidity percent per Clausius, Clapeyron, so photolysis and escape accelerate. The leak is slow at first, then faster. Pattern interrupt. Patience is the killer app of stars. So what's the visible sequence? First, harsher heat stress on land, longer humid nights and shifting cloud tops. Next, a stratosphere that refuses to stay dry. After that, hydrogen escape picks up, and over tens to hundreds of millions of years, the oceans thin. Coasts still look familiar for a long time, but the ledger is negative. By the time sea level change hints at mass loss, the biosphere is already in retreat. You might be asking, can geoengineering hold the cold trap? A carefully tuned sunshade trimming a few percent of flux could delay the leak by keeping the upper troposphere cooler and drier. But it's a maintenance program, not a cure. You're balancing a moving target as the sun keeps brightening. Miss a decade and the stratosphere can cross its wet threshold again. Curiosity gap. If a shade buys us time, does carbon still run out first? And that's the handoff. While the sky starts leaking, the rock thermostat keeps pulling CO2 down. Forests falter, grasses take over, then even they thin. The planet cools itself by deleting plant food. Coming up, the carbon drought, when photosynthesis loses the planet long before the last waves vanish. The carbon drought. Plants lose the planet. Here's the twist nobody expects. As the sky starts leaking, the rock cycle doubles down and starves the biosphere. The planet cools itself by deleting plant food. That's the carbon drought. Warmer, wetter conditions speed up silicate weathering. Rainwater plus CO2 makes carbonic acid. It reacts with fresh rock, and the carbon ends up locked in carbonates. More heat, more rain, faster kinetics, so atmospheric CO2 trends downward even as the sun pushes temperatures up. Curiosity gap. Hotter world, less greenhouse gas. How is that not self-correcting? Because biology has minimums and the thermostat doesn't care. Why this matters to you is immediate. Photosynthesis needs a floor. See 3 plants, the vast majority of today's forests and crops, struggle as ambient CO2 sinks toward their compensation point under heat stress. They respire to survive but can't net gain carbon. See 4 plants buy time with a CO2 concentrating trick and better water use efficiency. But buys time isn't wins. When heat and dryness rise while CO2 falls, even C4 systems hit their limit. Pattern interrupt. The planet's safety valve is using the biosphere as collateral. Let me make the thresholds concrete. Think in 2 collapses. First, the C3 crash. As CO2 drifts toward low hundreds of parts per million in a hotter, drier climate stomata, the leaf pores must open wider to pull in enough CO2, but that bleeds water. To avoid wilting, plants close stomata, which starves internal CO2 further. It's a lose-lose, breathe and bleed, or conserve and starve. Productivity tumbles, forests thin, nutrient cycles sputter, and oxygen production drops. Curiosity gap. When leaves stop breathing, what happens to Earth's air conditioner? Second, the C4 fade. Grasses built for lower CO2 availability and higher heat take over stripped landscapes, replacing forests with open, fire-prone biomes. They hold longer in arid zones and savannas because they sip water more efficiently. But push the thermometer high enough and dry spells long enough, and even C4 photosynthesis can't keep net gains. The biosphere compresses into refuges, high latitudes, uplands, coastal microclimates, caves. Food webs simplify, then fragment. The difference between living planet and surviving pockets is carbon availability. Once it falls below photosynthetic comfort ranges and heat stress rises, complexity unravels. Here's the part most people miss. Low CO2 and high heat multiply each other's damage. Hotter air increases vapor pressure deficit, dryness that forces wider stomatal opening for the same carbon intake. Wider opening loses more water, so plants close, which cuts CO2 uptake again. Each heat wave erases growth and recovery windows shrink. Aha moment, stress compounds. It's not additive, it's multiplicative. Now you might be thinking, can volcanism bring CO2 back? Over geologic time, yes, outgassing is the source. But in a warmed, rainy world, weathering and carbonate burial can outpace typical volcanic supply. Many long-term models tilt toward lower atmospheric CO2 as the sun brightens. You'd need sustained, elevated degassing or reduced weathering capacity, less fresh rock, less rainfall to reverse the trend. The star is pushing the other way. Quick mental model, 3 curves crossing. Solar brightness stair-steps up. Weathering capacity rises with temperature and runoff. Biological productivity rises, peaks, then declines as CO2 and heat stress bite. Where the weathering curve overtakes volcanic supply, atmospheric CO2 begins a glide toward the choke point. Hit that and forests don't just thin, they lose net assimilation. C4 picks up slack until heat and dryness crack that scaffold too. Pattern interrupt. When forests go, the planet trades leaves for dust. Common mistakes to avoid. Assuming oceans buffer land plants indefinitely, warm water holds less CO2, stratification weakens mixing, and weathering still buries carbon. Assuming fertilization fixes scarcity, adding iron or nutrients can't conjure ambient CO2, concentration limits remain. Assuming more leaf area always cools under stress, stomata stay closed, evap cooling drops and canopies heat. Curiosity gap, if transpiration fades, what happens to clouds over continent? Now the visible sequence you'd feel on the ground. Forest belts retract poleward and uphill. Savannas expand, then thin into shrublands and grasslands. Fire regimes intensify as fuels dry and storms spike lightning. Dust rises from bare soils, changing regional albedo and circulation. Rivers swing between flash floods and long trickles because soils lose structure without deep roots. Pollinators, herbivores, predators all ride the same down escalator as primary productivity fall. Here's the kicker: as vegetation shrinks, so does evaporative cooling. Less transpiration means fewer low clouds over land, more sunlight hits the surface, daytime highs spike and nights stay warmer under a moister sky. That amplifies the moist greenhouse march aloft. The 2 failure modes synchronize. Carbon scarcity starves the biosphere while humidity keeps the sky efficient at trapping heat. Aha moment. The leak above and the drought below aren't separate disasters. They're a lock and a key. Could geoengineering untie it? A modest sunshade could hold temperatures lower, slowing weathering and keeping the cold trapped drier, which helps both water and carbon. But it's maintenance forever. Miss the tune-up and the thermostat ratchets again. Biology never regains control of the dial once CO2 leans on the floor. Curiosity hook. If leaves can't cool the planet anymore, can the oceans still act as a flywheel? Or do they become the engine that speeds evaporation next? The ocean evaporation spiral. With forests fading and CO2 control weakening, the oceans step into the lead role, and not in a good way. Pattern interrupt, remove the flywheel and the engine shakes itself apart. Oceans are Earth's thermal mass. Thin that mass and the climate swings harder between day and night, summer and winter. Bigger swings mean higher peaks. Higher peaks mean more evaporation. Curiosity gap. Before a runaway, what's the unmistakable sign the leak has gone permanent? Watch the upper air. It won't dry out at night anymore. Here, SY stability dies first. A deep ocean mixes heat downward, smoothing out spikes. As volume effectively shrinks, surface layers warm faster, stratification strengthens, and the conveyor that once brought cold water up slows. Less mixing, more persistent marine heat waves, and evaporation surges over the warmest pools. That vapor doesn't just vanish, it piles into the lower atmosphere and throttles infrared cooling at night. Aha moment, you don't need a global runaway to feel like one locally. Humidity makes nights bad at being nights. Energy budget shift, plain language. Absorbed sunlight inches up. At the same time, low subtropical clouds can thin over warmer seas, letting more light in where you least want it. High anvils spread wider and higher, trapping heat aloft. The result is a dayside oven that runs longer each afternoon and a nightside radiator with a towel over it. Polar regions used to bleed heat efficiently. Now humidity spreads poleward and blunts that edge. Curiosity gap. If poles stop being the planet's heat sink, where does the excess go? Answer: deeper into the sky, faster towards space, but only after it does maximum damage below. Quick win intuition pump. Evaporating water consumes huge energy, latent heat is the tax. But as surface temperatures rise, each degree boosts air's moisture capacity roughly 7%, so payback accelerates. The ocean pays the tax from stored heat, the atmosphere pockets the vapor and uses it to block cooling. Pattern interrupt. The hotter it gets, the cheaper the next degree becomes. Here's where most people mess up, expecting rain to refill losses. The water cycle moves water, it doesn't mint new mass. Once hydrogen is escaping from the top, every thunderstorm is just shuffling a shrinking bankroll. In a warmer world, more rain tends to fall in short, intense bursts that can run off fast. Over land, that means flash floods, then dust. Over ocean, it just swaps ocean water for ocean water, while the leak to space continues aloft. Curiosity gap. If storms get stronger, why doesn't the planet cool more? Because evaporation plus high humidity often beats the radiative relief. Transport starts to break in familiar places. With weaker equator-to-pole gradients, jet streams wobble and stall. Heat domes park over continents. Marine layers thin along coasts as upwelling weakens in warmer, more stratified oceans. Fog belts that once moderated shorelines fade. Sea breezes hold on until the inland. Ocean contrast weakens, then they collapse too. Aha moment. A calm day at the beach becomes the hottest day of the year. What's the telltale sequence on the water? First, persistent marine heat waves in western boundary currents and subtropical gyres. Next, low cloud decks thin, nudging reflectivity down. Then, deep convective towers in the tropics routinely punch moisture into levels that used to be safe. The tropopause lifts and warms. The cold trap leaks more often. Satellite spectra show the stratosphere trending wet, orders of magnitude above today. That's the irreversible sign. Rain is no longer a round trip. Common mistakes to avoid. Counting on polar night to vent heat, moist air and high clouds undermine that advantage. Believing ocean currents will rescue coasts, stratification strangles vertical exchange. Assuming ice albedo can save you in reverse. Once seasonal sea ice is gone, there's little reflectivity left to gain. Thinking bigger day, night swings mean less total evaporation. Higher daytime peaks dominate the integral. Curiosity gap. Can dust from drying continents reflect enough sunlight to matter? Locally, yes. Globally, humidity still wins. So what's the lived outcome? A tighter spiral. Less ocean heat capacity yields larger extremes. Larger extremes drive more evaporation. More humidity slows cooling. Slower cooling raises the baseline. Higher baseline accelerates hydrogen escape. Coastal refuges hang on with sea breezes and marine layers until those weaken, then they flip. Interiors lock into heat. Humidity regimes that are physiologically hostile long before the last basins shrink. Pattern interrupt. The world ends steamy, not fiery. Could geoengineering dent this? A carefully modulated sunshade at L1, trimming a few % of flux, keeps the upper troposphere cooler and drier, propping up the cold trap and preserving low clouds over subtropical oceans. That can slow the spiral and delay the leak. But it's gardening, not a switch. You tend it forever while the star keeps brightening. Miss the maintenance and the spiral catches up. And right as the ocean flywheel wobbles, the sun is about to change state. Core hydrogen runs out, a shell takes over, and luminosity rises faster than any earthly system can buffer. Curiosity hook, same looking sun to your eyes, completely different engine under the hood. Leaving the main sequence, the quiet switch to Subgiant. This is the flip most timelines skip. No fireworks, no sudden color change, just the moment the sun's core runs out of hydrogen. Fusion in the very center stalls, the helium core contracts, heats, and a thin shell of hydrogen just above it lights up. That shell burns hotter and denser than core fusion did, so luminosity jumps while the outer layers begin to puff. Pattern interrupt. The on light stays steady. The dimmer quietly clicks brighter. Why this matters to you? Everything we've covered, moist greenhouse, carbon drought, the ocean spiral was battling a slow, predictable rise. The Subgiant Switch turns that slope into a staircase. Insulation steps up faster than weathering, clouds or circulation can compensate. If the stratosphere was flirting with wetness before, now it's a habit. If C3 plants were limping, they're done. Curiosity gap. If the sky still looks familiar, how would you know the thermostat just jumped a notch? Inside the star, the physics tightens. The helium core is supported increasingly by electron degeneracy pressure, so heating doesn't expand it much. That bottleneck focuses energy into the surrounding hydrogen shell, which burns more vigorously and dumps extra power outward. The envelope feels that push, expands, and cools a little at the surface, slightly redder spectrum, but the larger area more than compensates. Net, higher total power. Aha moment, redder doesn't mean weaker. Bigger surface wins. Here's the external tell, if anyone were around to see it. Days grow harsher and nights stop helping, even more than before. Subtropical low clouds thin further, high anvils linger, and marine fog belts fade along coasts as upwelling weakens. Dust lifts over continents stripped of deep roots. Ozone repair falters because humidity feeds HOC's radical chemistry that can destroy ozone, and increased solar output provides more energy to drive photolysis. Pattern interrupt. The blanket gets heavier exactly when the radiator shrinks. Most people think the red giant is the starting gun. The subgiant phase already ends surface habitability. You don't need giant star luminosities to finish oceans and erase complex ecosystems. A sharper insulation rise guarantees the cold trap stays weak, so stratospheric water mixing ratios remain high and hydrogen escape locks in. Meanwhile, with less liquid water cycling through soils and rivers, silicate weathering style shifts, less fluid-driven, more thermal and aeolian, but the earlier CO2 drawdown already starved the biosphere. Curiosity gap. Could a planetary sunshade keep up with a faster rising star, or does control lag doom the fix? Let's stress test the levers. A shade at L1 that trimmed, say, a few percent of flux might match slow main sequence brightening with steady maintenance. In subgiant mode, you need tighter control loops, faster replacement, and more margin for solar storms and radiation pressure. Mismaintenance windows and the stratosphere crosses wet thresholds again. Orbit moving via asteroid assists. That's a cadence game over millions of years. A steeper climb in luminosity shrinks your slack. Aha moment. Geoengineering shifts from hard to harder and faster. Spectrum matters in sneaky ways. A slightly cooler photosphere emits a larger fraction of energy in near-infrared bands that water vapor and CO2 absorb well. So in a moist atmosphere, additional power can couple efficiently into absorption bands. The air column can warm disproportionately aloft, raising greenhouse opacity and helping to lock in a wet stratosphere. Even if total brightness didn't spike, that spectral tilt would still sting. Pattern interrupt. The star changes the channel to the one your atmosphere likes to watch. Common mistakes to avoid. Assuming orbital period or day length gives it away, those barely budge here. Expecting volcanic winters to offset steps, sulfate aerosols fall out in years, the forcing step is permanent. Banking on deep aquifers and caves, useful refuges for a while, but they depend on surface recharge and dwindling productivity. Believing magnetospheres block escape, helpful against particles, not against energy-limited hydrodynamic outflow when EUV and total power rise together. Curiosity gap. If radiation belts intensify, does that halt loss or just move it to the poles faster? So what does life look like at this point? Surface oceans are fragmented or gone. What remains are hot brines in shadowed niches that evaporate seasonally. Atmosphere is thin on volatiles, thick on dust and mineral vapors after heat waves. Photosynthetic ecosystems have collapsed into extremophile pockets, microbial mats in sheltered cracks, perhaps living off chemistries we once ignored. Those pockets don't influence climate anymore. Physics is driving. The biosphere stops being the air conditioner and becomes a footnote. Could any strategy buy a sliver more time? A hybrid. Maintain a dynamic L1 shade with overcapacity to track the steeper rise, while slowly nudging Earth outward with meticulously choreographed asteroid flybys. The shade buffers fast changes. The nudges pay down long-term flux. But this demands a maintenance culture measured in millennia, with autonomous factories printing replacement films from lunar and asteroid feedstock, and governance that treats entropy as a monthly bill. Miss payments and the star collects. Here's the clean mental model to leave with. The Subgiant Switch is the mortgage reset on a planet already living paycheck to paycheck. Your bills jump overnight, your income doesn't. You sell assets, oceans, CO2, clouds to stay afloat, but the interest compounds faster. Aha moment, after this switch you do stabilize, you manage decline. Next up, the drama everyone recognizes. The red giant surge where mass loss, tides, and drag start tugging at orbits. But remember, the story of habitability ended here, quietly, with a sun that still looked familiar to the naked eye. Curiosity hook. Can mass loss push Earth outward fast enough to dodge a swollen photosphere, or do tides win the last tug of war? Humanity's only levers. Orbit tricks, shades, and moves. If habitability ends early, we don't negotiate with geology. We edit sunlight or we move the world. That's it. Pattern interrupt. Planting trees isn't a lever here. Sunglasses and steering wheels are. Curiosity gap, which buys more time per kilogram, shading Earth or nudging its orbit. Start with the cleanest watt per kilogram lever. A solar shade near Sun, Earth L1. L1 sits about 1.5 million kilometers sunward, where gravity and orbital motion balance just enough for a craft to hover in a halo path. You don't need a monolithic disk. You need an ensemble of ultra-thin films or diffractive meshes that trim a few percent of sunlight. Aha moment, we're not dimming the sun, we're shaving the excess. Why this matters: if luminosity rises 10%, Earth's absorbed average climbs roughly 24 WM2. Cancel that and you hold the cold trap, slow weathering, and delay the moist greenhouse. A diffractive shade can lean into radiation pressure to stay in position, tilt the film, let photons both push and hold station, and fly a controlled halo. Swarms spread risk. Lose a few, the fleet still works. Curiosity gap. If a 2% trim stalls the leak, why is that the end of the story? Because maintenance is the story. The thing most people miss. Shades are gardens, not monuments. UV embrittles polymers, micrometeoroids pepper holes, radiation pressure acts, and halo dynamics drift. You need constant replacement. The shortcut nobody teaches is to move manufacturing off Earth. Print films from lunar aluminum and silicon, spool kilometers of mesh in cislunar factories, and send replacements on a cadence. Pattern interrupt. The thermostat is a supply chain. Could dust do it cheaper? A lunar sunscreen cloud placed near L1 or along resonant orbits can shade broadly with minimal mass per particle. It also blows away fast, radiation pressure, pointing Robertson drag solar storms, you're refilling constantly. Think orbital sunscreen misting, clever, relentless, failure-prone if you miss a season. Shades give control, dust gives diffusion with a steep upkeep curve. What about stratospheric aerosols? They can offset a few WM2 for years at a time, handy for today's warming, not a geological pension. They mess with hydrology and ozone chemistry and they settle out. Useful bridge, not a civilization's forever plan. Curiosity gap. If shades are viable, why risk orbital nudging at all? Because the star keeps brightening, you want a second lever that compounds. Inter-orbit moves. Flux drops as 1 over distance squared. If the sun brightens 10%, push Earth's semi-major axis out by roughly 4.8% to break even. That's on the order of 7 million kilometers at 1 AU. You don't strap rockets to continents, you trade momentum with asteroids. This is gravity billiards. Here's how the shepherding game works. Redirect a massive asteroid so it passes behind Earth relative to our motion. Gravity tugs both ways. The asteroid slows slightly, Earth speeds up, and our orbit grows. Then send the asteroid to Jupiter for an energy top-up and repeat. Thousands of carefully choreographed passes over millions of years add centimeters per second to Earth's orbital velocity. Exactly what you need. Aha moment, small pushes, absurd patient. Now the part that separates sci-fi from engineering, risk and cadence. You need tugs, solar sails, or nuclear electric to shape each asteroid's approach years in advance, protected corridors for flybys, and autonomous aborts if geometry slips. Miss by fractions and you turn a planetary seatbelt into an impactor. Governance isn't optional, it is the actuator. Pattern interrupt. Orbital mechanics is the easy half. Trust is the hard half. Quick win mental math. A 5% orbital increase over 10 million years is 0.5% per million. Spread out, you're aiming for aggregate Earth delta V on the order of centimeters per second per millennium. That's within reach of a long sequence of 1,000-kilometer class bodies under precise guidance. Curiosity gap. If you can move Earth, why not just build new homes elsewhere? Spoiler, you should at the same time. Shades versus moves isn't either or, it's both and. Shades are agile. They handle year-to-year variability, solar storms, and the steady brightening. Orbit nudges are slow capital. They pay dividends forever. The game changer nobody talks about is control margin. You don't cancel the exact excess. You overshoot a bit and modulate, like cruise control with buffer. That demands extra mirror area and tight attitude control. It also demands repair. Swarms must replace themselves without begging Earth for parts. Common mistakes to avoid. Believing one nation can run the thermostat. Fragmentation kills maintenance. Underestimating debris. Thin films can shred. Swarms need fail-safe end-of-life modes. Treating L1 like a parking lot. Radiation pressure means you fly displaced halos, not static points. Ignoring spectral tilt. A redder sun couples better to near-infrared absorbers. Shades that diffract can tune spectral cutoffs for maximum cooling per gram. Curiosity gap. What if shades fail for a decade? The cold trap can cross its wet line and catching up gets harder. So what's the play for a serious species? Build a maintenance culture now while it's optional. Start small. Demonstrator shades that modulate 0.1% for a week. Autonomous film printers in cislunar space. Safe rehearsal of microasteroid momentum trades far from Earth. Then scale. A percent-level shade with redundancy. A long-term asteroid shepherding program with international oversight and kill switches. Industrial habitats off-world to bootstrap your supply chain. And parallel track and exit lane. Free space habitats let you set gravity by spin, tune day length, and migrate outward with the isotherms. If shades hiccup, habitats persist. If nudges slow, habitats move themselves. Aha moment, the best way to protect a planet is to stop needing it. Final sanity check. Could any of this beat the red giant? No, these levers buy time, tens to maybe hundreds of millions of years if you run them flawlessly. That's a victory measured in civilizations. Pattern interrupt. We don't outlast the star, we outlast our excuses. Curiosity hook. Next, the red giant surge. Mass loss tugs orbits outward while tides pull inward. Which force decides if Earth is swallowed? Red giant ascension. The sun bloats, orbits shift. Now the furnace really turns up. Pattern interrupt. The light gets redder, the star gets bigger, and gravity gets weaker. Hydrogen shell burning races around an inert helium core, dumping far more power outward than core fusion ever did. The envelope swells to colossal size, surface temperature drops a bit, but the radiating area explodes, so total luminosity surges. Curiosity gap. Does a weaker surface really mean more heat for us? Yes, bigger surface beats cooler color. Why this matters to you? Swollen stars don't just bake planets, they move them. As the sun sheds mass in a dense, dusty wind, its gravity slackens. Orbits respond by expanding. Semi-major axes grow roughly in proportion to 1 over the remaining solar mass. That's the outward tug. But there's a rival, tides and drag. A bloated envelope raises tides on anything nearby, dissipating energy and pulling orbits inward. If the extended atmosphere brushes a planet's path, aerodynamic drag adds a brake. Aha moment. 1 force pushes you out, 2 pull you in. Let me give you the tug-of-war in plain language. Mass loss is gentle but relentless. It makes the gravitational well shallower, letting Earth drift outward. Tides are weak at first, then spike late when the sun is huge and its convective envelope dissipates efficiently. Drag is negligible until the photosphere and exosphere swell into your lane, then every pass through thin gas bleeds momentum. Curiosity gap. Which side wins for Earth? Escape by drift or capture by drag? It's a razor's edge. Here's the cinematic sequence most people never see coming. Mercury and Venus don't get a vote. Even with mass loss, the sun's radius on the upper red giant branch overshoots their orbits. They're engulfed, slowed by drag inside the envelope, and spiraled down. Earth sits near the threshold. If mass loss ramps early and fast, our orbit can expand enough to dodge the photosphere's maximum reach. If envelope growth and tidal dissipation lead, we skim gas, lose angular momentum, and the plunge begins. Pattern interrupt. Survival here means not swallowed, not habitable. Spectral tilt adds insult. A cooler photosphere emits a bigger fraction in the near-infrared, wavelengths water vapor loves to absorb. Even before contact, each extra watt couples more efficiently into a moisture-rich atmosphere. If any volatiles remain, they're heated harder per watt than before. Meanwhile, the stellar wind transforms into a gale. Mass loss rates jump orders of magnitude, and the dense, dusty outflow batters any remaining atmosphere with sputtering and ion pickup. Magnetospheres shape the flow. They don't stop energy-limited escape at these inputs. Now the orbital mechanics twist nobody talks about, eccentricity. As solar mass drops, resonances among the planets migrate. Anisotropic outflows and shifting gravitational couplings can pump eccentricity slightly. A more eccentric Earth means perihelion dips closer just when the sun is largest, spiking tidal forces and heating. Those perihelion passes are when tides and drag take the biggest bites. Curiosity gap. Could a small eccentricity change tip the outcome? Yes, because tides scale nonlinearly with distance. Common mistakes to avoid. Treating mass loss as a uniform rescue, it helps distance, but not if tides wake up late. Assuming engulfment is instant vaporization, drag and heating tear a planet down over many orbits. It's quick geologically, not cinematic seconds. Ignoring tidal heating in the planet, flexing adds internal heat to a world already scorched. Believing dust cools you, nearby dust absorbs starlight and re-radiates in infrared. It can warm surfaces that absorb IR well. Aha moment. The inner system becomes a radiant oven wrapped in moving sand. So what's the likely storyboard for Earth? 2 plausible endings. In one, mass loss pushes us outward just enough that the swollen photosphere never quite reaches our path. We survive physically as a bone-dry, atmosphere-free rock on a wider, perhaps more eccentric orbit around a blinding, bloated sun. In the other, late-stage expansion plus efficient tidal dissipation drags us into the envelope. Once inside, drag converts orbital energy to heat in the stellar gas, the orbit shrinks, and we spiral down. The difference hangs on details: the exact mass loss law, the sun's tidal quality factor, and timing. Pattern interrupt, tiny assumptions, planetary consequences. Meanwhile, the inner system dissolves. Mercury and Venus disappear. Asteroid belts get stirred as resonances sweep outward, sending debris both in and out. Some bodies are captured into decaying orbits and shredded, others are flung to colder pastures. The zodiacal cloud thickens with dust, turning daylight into a copper haze if any surface eyes were left to see it. There won't be. Quick win marker. If you could track it from afar, you'd see the sun's apparent size grow and its color redden, but the total brightness at Earth's moving orbit spike and then spike again. You'd watch perihelion passages glow hotter than aphelion by a margin that keeps growing, a sign eccentricity is quietly rising. You'd also see spectral lines from dust and gas in outflow, evidence of the wind doing the sculpting. Could any lever help this late? Not really. Shades can't offset orders of magnitude luminosity increases. Orbit nudging is too slow to outrun a swelling photosphere on million to multi-million year timescales. The only help is the sun's own mass loss pushing you outward, and that's not a policy, it's a coin flip. Curiosity hook. After this surge, the star's core is about to reset from within, the strangest quiet blast you'll never see. Atmospheric escape and stripping. Here's the brutal part most timelines glide past. Once the sun swells and the wind howls, the sky doesn't burn off, it's vacuumed from the top down. Pattern interrupt. The atmosphere leaves like a river flowing upward. Curiosity gap is a magnetic field, a shield, or a funnel when the storm is the sky. Start at the top. High-energy solar radiation floods the upper atmosphere, ionizing gases and superheating the thermosphere. Temperatures can jump to thousands of Kelvin, scale-height balloons, and the exabase lifts to altitudes where gravity's grip is weaker. That's the setup for hydrodynamic escape, heated gas expanding outward as a bulk flow, dragging heavier molecules by collisions. Aha moment. This isn't a few atoms sneaking away, it's the whole upper sky loosening and lifting. Energy is the bottleneck. If high-energy input exceeds what the atmosphere can radiate and conduct downward, the only pressure valve is outflow. Escape becomes energy-limited, roughly scaling with the incoming high-energy flux divided by the gravitational binding per molecule. Earth's gravity helps, but not enough against the intense radiation and wind environment of late stellar phases. Curiosity gap. Can night-side cooling fix it? No, circulation moves heat, and the exabase cares about global balance, not midnight relief. Now the solar wind turns from breeze to battering ram. A dense outflow of charged particles slams the exosphere, sputtering atoms directly and picking up ions that get swept down magnetic field lines. Ion pickup is a thief with leverage. Once neutrals get ionized, the wind's magnetic field grabs them and flings them away. Sputtering adds insult. Energetic ions knock atoms free from the upper atmosphere and even from volatile-rich surfaces. Pattern interrupt. The wind doesn't just blow, it sandblasts. What about the magnetosphere? Most people think force field, full stop. The thing they miss is geometry. A strong field does deflect a portion of the wind and expands the obstacle, buying time, but it also funnels power into the polar caps through open field lines. Under extreme forcing, reconnection opens wide polar throats. Outflow can jet from auroral zones, not just the equator. Shields help shape lost pathways. They don't cancel energy-limited escape when the burner is high. Aha moment. The magnetosphere trades wall for valves. Chemistry collapses with the structure. Ozone depends on oxygen UV and a delicate dance with radicals. In a steam-laden, UV-bright upper atmosphere, water photolysis produces HOX that tears through ozone. With photosynthesis gone, oxygen supply dwindles, production can't outrun destruction. Ozone thins, then vanishes, letting deeper UV drive photolysis lower. Curiosity gap. Does leftover oxygen pile up from water loss? Not for long. Oxygen reacts with rocks and surface minerals, and sputtering strips a share to space. Common mistakes to avoid. Assuming heavier gases automatically stay, hydrodynamic flow can tow them along. Believing dust in the inner system cools you, nearby dust absorbs starlight and re-radiates infrared, warming surfaces that love IR. Counting on episodic volcanic outgassing, new volatiles become fodder for photolysis and pick up almost as fast as they emerge. Let me give you the telltale diagnostics. If anyone were around with instruments, you'd see the exosphere swollen, the bow shock pressed close by a dense wind, and auroral ovals blazing nearly continuously. Mass spectrometers would register enriched heavy isotopes as lighter species preferentially escape, an atmospheric fingerprint of loss. Spectra would show diminished ozone bands, enhanced hydrogen and oxygen emissions from dissociation, and a hot iron tail streaming anti-sunward. Thumbnail moment: Earth trailing a comet-like iron plume. Surface conditions lock in the end state. With volatiles stripped, any residual atmosphere hugs the ground as mineral vapors and trace heavy gases from outgassing. Sputtering gnaws at frost and hydrates. Thermal spikes liberate pockets that vanish upward. Without a dense air column, day-night swings are savage but irrelevant to escape. There's no reservoir left to save. Pattern interrupt. The sky is no longer weather, it's inventory. Could any lever matter here? Shades can't cut UV enough relative to visible without absurd mass. Diffractive designs help, but not at the orders of magnitude you'd need this late. Magnetospheres, useful earlier, overwhelmed now. The only win is earlier prevention. Keep the cold trap dry, keep oceans deep, keep CO2 high enough for plants to run the air conditioner longer. Curiosity hook. The star is about to fix its own instability in the strangest whisper, a core reset you won't see coming. Helium flash, and the red clump pause. Here comes the strangest quiet blast you'll never see. Pattern interrupt. The star's biggest bang barely changes the surface for a moment. Deep inside, the helium core has been squeezed into degeneracy, where pressure ignores temperature. Heat it and it doesn't expand to cool. Curiosity gap. What happens when fuel lights in a core that can't relieve pressure by puffing up? It runs away fast. That ignition is the helium flash. In seconds to minutes inside the core, helium fusion roars on via the triple alpha process. Almost all that energy goes into lifting degeneracy and expanding the core, not into the surface. Aha moment. The star fixes its instability by spending the flash's energy turning a locked spring into a working piston. To distant eyes, luminosity doesn't explode. The envelope barely flinches at first. Why this matters to you? The flash is the pivot that takes a chaotic, swelling red giant and parks it into a steadier gear. As the core expands slightly and cools, helium burning stabilizes. Hydrogen keeps burning in a shell outside. The envelope responds by contracting from its maximum red giant bulk. The sun shifts to the horizontal branch spot for solar mass stars, the red clump. Pattern interrupt, not a reset to normal, a plateau, it's still lethal. Here's the red clump reality. Luminosity drops from the tip of the red giant branch to a lower, steadier level, but it's still many times today's sun. Radius shrinks compared to peak. Surface temperature ticks up a bit. The spectrum shifts slightly bluer than the maximum giant phase. Curiosity gap. Does this lull help any surviving worlds? It calms the wind relative to the peak, but the furnace stays on. Escape and sputtering keep stripping volatiles from any exposed surfaces. For Earth, if anything remains, it's a bare mineral shell long past habitability. The game changer no one talks about is duration. The clump endures on the order of 100 million years for a sun-like star, long compared to civilizations, short compared to the main sequence. That's enough time for the system to rearrange again under gentler but persistent forces. Orbits that expanded during the violent red giant wind now drift outward more slowly as mass loss eases. Tidal torques weaken with the contracting envelope, reducing the inward pull that threatened marginal survivors. Aha moment. It's a plateau in stellar temperament, not in planetary safety. We make the internal engine clear. Triple alpha fuses 3 helium nuclei into carbon. Some carbon captures helium to make oxygen. The core now has a thermostat again. Heat makes it expand, expansion cools it, so burning regulates. Meanwhile, the hydrogen shell keeps feeding helium ash inward, slowly growing the carbon-oxygen core. Each photon of power you see is the consequence of a balanced assembly line. Shell adds helium, core burns helium, envelope transports energy outward. Curiosity gap. Does that balance ever hiccup? Not here. The hiccups return after helium runs out. External tells you'd measure from a surviving probe. A bright, still bloated sun with a slightly higher effective temperature than at the red giant tip, a dense but steadier wind, and a thick infrared glow from lingering circumstellar dust seeded during the prior superwind. The nebula isn't lit yet. The envelope hasn't detached. Resonances in the outer system keep wandering as solar mass continues its slow decline. Small nudges still destabilize minor bodies over clump timescale. Pattern interrupt. The sky looks calmer while the chessboard keeps shuffling. Common mistakes to avoid. Thinking flash means external fireworks. Almost all energy stays inside to lift degeneracy. Believing the clump is a breather for planets, luminosity remains far above present day and any atmosphere is gone. Assuming dust now cools survivors, local dust absorbs starlight and re-radiates infrared. Surfaces that love IR get warmed, not saved. Expecting magnetospheres to rebuild skies, they can channel particles, not conjure mass against steady EUV. So what's the lived consequence for a dead Earth? None, no oceans, no air, just thermal cycles on exposed rock. For the solar system, the clump is the long exhale before the last storm. The star coasts on helium until the tank runs dry. Then the thermostat fails again, double shell burning returns, pulsations grow, and mass loss skyrockets. Curiosity hook. What turns a steady, bright clump star into a dust-making giant that breathes in pulses you can see across light years? Answer, the asymptotic giant branch. When the envelope swells larger than ever, thermal pulses thump through the star, and the wind turns into a superwind that builds the planetary nebula to come. Pattern interrupt. The funeral veil starts forming while the star is still alive. Asymptotic giant branch. The sun sheds its skin. Now the calm breaks again. Pattern interrupt. The star starts breathing deep, dusty breaths. When core helium runs out, the sun can't keep that steady burn. The core, now carbon and oxygen, contracts and heats. Helium reignites in a shell above it. Hydrogen burns in a shell above that. Double shell burning is unstable. Curiosity gap. What happens when fuel is lit in two stacked layers under a loose blanket? Pulses, thermal pulses that make the star inhale and exhale. Here's the rhythm. Every tens of thousands of years, helium shell burning spikes in a thermal pulse. The envelope puffs out, cools, then slowly contracts as the pulse fades. Convection dredges deep layers upward, hauling carbon and S-process elements to the surface. Aha moment, the sun turns itself into a dust factory. If the surface flips carbon-rich, the wind condenses graphite and silicon carbide. If it stays oxygen-rich, silicates dominate. Either way, dust forms, photons push dust, dust drags gas. The wind becomes a superwind. Why this matters to you? Mass loss accelerates by orders of magnitude. The sun sheds its skin fast enough that planetary orbits expand significantly as gravity weakens. That's the outward tug. But the dense wind also acts like a slow brake on anything with cross-section. Small bodies spiral, larger survivors plow through grit and plasma each orbit, losing a whisper of momentum every pass. Pattern interrupt. The system becomes a sandblaster with gravity turned down. The game changer nobody talks about is the pulse-driven chaos. Luminosity, mass loss rate, and wind density step, not slide. Each pulse tweaks the solar mass and envelope, which nudges gravitational parameters and drags. Resonances migrate in jumps. Asteroid families decohere. Comets get jostled from reservoirs. Collisional cascades light up, feeding even more dust just as radiation pressure is most effective at lofting it. Curiosity gap. Does that dust cool anything? Locally, it can provide shade. Globally, it tends to absorb starlight and re-radiate infrared, warming surfaces that absorb IR well. Let me make the engine legible. Double shells feed energy into a huge convective envelope. Convection dredge-up episodes mix newly made carbon into the photosphere. Enough dredge up and the sun becomes a carbon star at the surface. Not enough and it stays oxygen-rich. That chemistry sets the kind of grains the wind grows. Grain opacity matters because radiation pushes on grains far better than on gas. Grains take the photon shove, transfer momentum to gas by collisions, and the whole outflow accelerates. Aha moment. Photons are the propellant, dust is the sail. External tells you'd measure from a far probe. A cool, enormous star with dramatic infrared excess from a thick circumstellar envelope. Episodic brightenings tied to thermal pulses, an outflow speed in the tens of kilometers per second, and layered shells, fossils of past pulses, moving outward like tree rings in space. The bow shock where this superwind meets the interstellar medium glows faintly, a sign the sun is carving a bubble. Pattern interrupt. The funeral veil starts forming before the funeral. What about Earth's fate in this gale? If we dodged engulfment earlier, mass loss here pushes our orbit farther out. That helps distance. It doesn't restore habitability. The wind pounds any remaining volatiles with sputtering and ion pickup. Late outgassing from heated crust, photolized and torn away almost as fast as it emerges. Tidal torques can reawaken near periastron if the envelope swells far enough, but pulses tend to contract and expand the envelope on timescales short compared to secular orbital drift. It's a race you don't want to be in. Curiosity gap. Could a small eccentricity nudge suddenly tip us into the envelope on a pulse crest? On the knife edge, yes. Common mistakes to avoid. treating the AGB like a brighter red giant. No, the double shell instability and dredge up make it a different beast. Assuming dust equals cooling, nearby dust heats by IR re-emission. Cooling wins only for far observers. Believing big planets are immune, drag per pass is tiny, but millions of passes add up, and tides with a bloated star can still sting. Thinking this phase is brief. The AGB lasts long enough to unbind a massive fraction of the envelope and to rewrite the inner system's architecture. Here's the visible sequence, step by step. First, winds thicken, the infrared glow swells. Next, a thermal pulse spikes luminosity, the envelope puffs, and a new dusty shell lifts off. Between pulses, the star dims a little and contracts, but mass loss never stops. Shells overtake shells, creating knots and arcs in the outflow where faster wind runs into older, slower material. Farther out, those structures seed the planetary nebula's future filigree. Aha moment! Today's dust is tomorrow's glow. Could any lever help now? Shades can't cancel this much power or fix EUV selectivity. Orbit nudging is too slow against pulse scale changes. Magnetospheres shape plasma streams, but can't defend against energy-limited escape or sputtering at these fluxes. The only leverage was earlier, keeping the cold trap dry, holding CO2 in a biosphere-friendly band, and building off-world capacity before maintenance became mandatory. Pattern interrupt. Prevention was planetary, cure is stellar, and we don't do stellar. So what's the payoff? The sun is actively building its own museum piece. Each pulse breathes another layer into space, and the envelope thins. When the veil gets tenuous enough, ultraviolet from the hot core will leak out, strike the shells, and make them glow. That's the planetary nebula you've seen in posters, not a planet but a tomb lit from within. Curiosity hook, what flips that switch from dusty wind to glowing ring? Answer, the envelope finally detaches, the hot core's temperature spikes, and UV floods the cocoon. The funeral is the brightest scene, and then the lights go down as the core cools into a white dwarf. Planetary nebula and white dwarf. The last light. This is the part people call beautiful because it is. Pattern interrupt. The funeral is the brightest scene. When the envelope finally thins, the hot core peeks through and floods the dusty cocoon with ultraviolet. Curiosity gap. What happens when invisible light hits a shell of stellar breath? It glows, hydrogen, oxygen, and nitrogen lines lighting up like neon. That's a planetary nebula, not a planet, but a star's last letter written in gas. Why this matters to you? The nebula is a clock with a short hand. The gas must stay dense enough to shine while the core is still blazing hot. As the shell expands, it thins. As the core cools, the UV fades. The overlap is the show, tens of thousands of years, a blink in stellar time, but long enough to etch rings, knots, and arcs that record every pulse the star took on the AGB. Aha moment. Today's dusty shells become tomorrow's glowing filigree. Here's the physics in plain language. The exposed core runs scorching hot, tens of thousands of Kelvin, so its UV ionizes the escaping gas. Electrons recombine with ions and emit light at specific wavelengths. Hydrogen, S-bomber lines, oxygen's green and blue, nitrogen's red. The expansion speed is steady, tens of kilometers per second, so the nebula balloons to light-year scales while fading. Radiation pressure shapes it, magnetic fields and binaries sculpt it. Earlier pulse shells create layered rings that look like ribs in space. Pattern interrupt. It's a firework you can watch for millennia. Now the handoff to the final star. The core, stripped to its carbon-oxygen heart, is now a white dwarf, roughly Earth-sized, half the sun's mass and supported by electron degeneracy pressure. Curiosity gap. With no fusion, what keeps it shining? Stored heat. It radiates away its thermal energy, cooling from white to red to black over billions of years. No more thermostat, no more fuel, just an ember. Let me give you the signature you demeasure. Surface gravity is extreme. Escape speeds are thousands of kilometers per second. Spectra show a hot, blue-white continuum at first, then a slow slide toward the infrared. Many white dwarfs have polluted atmospheres, heavy elements like calcium or iron, evidence that surviving debris wandered too close, got tidally shredded inside the Roche limit, and rained onto the surface. Aha moment. You can read pulverized planets in a dead star's light. What's happening to the system around it? With the envelope gone, the gale calms. Orbits that expanded during mass loss stabilize around a smaller gravitating mass. Survivors, outer planets, dwarf planets, large asteroids, circle a point of light that gives no seasons, no weather, just a steady glow that weakens over eons. Resonances have migrated, belts are stirred. comets still fall inward on destabilized paths, feeding dusty rings that briefly brighten the dwarf in infrared. Pattern interrupt. The chaos is over, the attrition continues. Common mistakes to avoid. Thinking the nebula lasts ages, it disperses into the interstellar medium on short cosmic timescales. Believing the dwarf is fragile, it's dense, locked by degeneracy, and stable unless pushed to extreme mass. Assuming habitability returns at farther orbits, luminosity is too low for old inner system distances, and there's no air or water left to work with. Curiosity gap. Is there any second act for life here? Not around this remnant. The energy budget is a nightlight, not a heater. Here's the clean mental model to keep. The planetary nebula is the epitaph, brief, luminous, and full of structure that remembers the star's last breaths. The white dwarf is the tombstone, the memory of mass in a compact bead the size of Earth. Over billions of years, the dwarf cools. Its interior may crystallize, releasing a little latent heat and pausing the fade, but not stopping it. Eventually, the nebula dissolves into the galaxy, seeding future stars with carbon and oxygen the sun forged and exhaled. So what's the story beat that ties back to us? The ending is quiet because the deadlines that mattered were earlier. We lost oceans in a slow leak, not a boil. We lost plants to carbon drought, not a blaze. We crossed thresholds while the sun still looked familiar. The nebula is the spectacle, the white dwarf is the coda. The tragedy happened off stage, long before the curtains of gas lit up. Final pattern interrupt. The universe keeps the receipts. Those glowing shells will drift, mix, and someday help build new worlds around calmer stars. If we learn maintenance and patience, we can ride that cycle, build habitats that move, shades that hold, and cultures that outlast brightening suns. Curiosity hook for what's next. How long could a serious species stretch the clock? Millions, tens of millions, or more? And which lever buys the most future per gram? The human horizon. Deadlines that matter to us. Let's put the clock on human timescales. Pattern interrupt. The star's drama is billions of years away. Our deadlines walk up quietly in the next few 100 million. Curiosity gap. Which hits first for people? Leaking skies, starving plants, or heat you can't sleep through? First checkpoint. Productivity slides before oceans vanish. As solar output creeps roughly 1% per 100 million years, background warming trims atmospheric CO2 via faster silicate weathering. C3 plants, the workhorses of forests and many crops, struggle as CO2 drifts toward their compensation point under higher heat and vapor pressure deficit. You still get blue oceans and seasons, but less net growth, thinner forests, and oxygen production trending down. Aha moment. Food webs feel this long before coastlines look strange. Second checkpoint, the stratosphere stops being dry. That's the moist greenhouse onset, the point of no return. The threshold is subtle. Stratospheric water jumps orders of magnitude from today's few parts per million. You won't see ocean levels drop, you'd see it in spectra. Hydrogen begins a slow, permanent escape. Pattern interrupt. The first irreversible loss is invisible to your eyes. Third checkpoint, the C3 collapse, then the C4 era. C4 grasses hold on with better water use efficiency and CO2 concentration, replacing forests with open, fire-prone biomes. But later is forever. Heat and dryness compound. Even C4 net gains falter as recovery windows shrink. Curiosity gap. Can we engineer crops past physiology? You can shift thresholds, not the floors. Fourth checkpoint, the ocean flywheel thins. Marine heatwaves persist longer, low subtropical clouds retract, and humid nights stop radiating away heat. Interiors lock into heat, humidity regimes that break human physiology outdoors. Coastal refuges last longest with sea breezes until upwelling weakens and fog belts fade. Aha moment. Nights stop rescuing days. Fifth checkpoint, the Subgiant Switch. The sun's core hydrogen runs out, shell-burning lights, luminosity steps up. The sky still looks familiar, which is the trap. Insulation rises faster than any earthly feedback can buffer. Whatever wasn't already lost gets finished. Ozone chemistry, surface water, the last stubborn ecosystems. Pattern interrupt. The thermostat jumped. Your eyes didn't notice. So what's actionable now? 3 tracks: maintenance, mobility, and margins. Maintenance means learning to modulate sunlight. A swarm shade at L1 trimming a few percent buys time. Colder upper troposphere, drier stratosphere, slower weathering, delayed moist greenhouse. The trick nobody teaches, it's not a monument, it's a garden. You build autonomous factories in cislunar space, print diffractive films from lunar and asteroid feedstock, and replace segments constantly. Curiosity gap. What if the fleet pauses for a decade? The cold trap can cross wet, and catching up gets harder. Mobility means orbit options. Slow, safe asteroid shepherding nudges Earth outward centimeters per second per millennium. Shades handle year to year, nudges pay down the long term. Risk lives in cadence and governance, protected corridors, redundant tugs, and hard aborts. Aha moment. The physics is easy compared to keeping humans coordinated for millennia. Margins mean decoupling life from a fussy sky. Free space habitats set gravity by spin, day length by shutters, and climate by design. Start near Earth for logistics, migrate outward to follow comfortable flux as the sun brightens. Habitats make shades less existential. If the fleet hiccups, cities in space survive. Pattern interrupt. The best resilience is not having all your biology under one thermostat. Common mistakes to avoid. Waiting for perfect drives, closed-loop life support, and repair cultures matter more than speed. Betting on aerosols for geological times, useful as a bridge, not a pension. Assuming volcanism will refill CO2, too slow against enhanced weathering in most models. Treating governance as a footnote, trust is the actuator. What about Earth refugia? Steward high latitude and upland arcs where cooler, wetter microclimates persist longest. Build cold chain seed vaults and genomic libraries that outlive politics. Harden freshwater networks against swingy hydrology. Store during deluge, ration through flash droughts. Curiosity gap. If leaves can't cool continents, can machines? Locally, yes. District-scale evaporative and radiative cooling strategies can help people, not the planet. Timeline sanity bands matter. Models disagree on exact dates, but the ordering holds. Productivity down, sky wet, C3 fail, C4 fade, ocean flywheel wobble, subgiant step. The lesson isn't panic, it's pacing. Start maintenance while it's optional. Prototype shades at 10th% scale. Rehearse micro-asteroid momentum trades far from Earth. Spin up orbital industry before it's the only way to breathe. Key mindset shift from heroics to habits. Shades, habitats, and nudges aren't stunts, they're utilities. Build them like power grids and water systems, with redundancy, inspections, and boring dashboards that stay green. Aha moment. The civilization that survives treats entropy like a monthly bill. Final pattern interrupt. We don't beat the star, we beat the calendar. By millions of years with shades and nudges, by options with habitats, by wisdom by practicing now. Curiosity hook, which lever buys the most future per gram. Next, we run the math and pick the first move. Plan B, off-world habitats and stellar hopping. If the planet turns into a maintenance project, Plan B is simple to say and hard to do. Stop needing one specific world. Pattern interrupt. Think neighborhoods that fly, not continents that sink. Curiosity gap, which scales faster, fixing a planet's thermostat or building cities in space. Start with the fastest path to livable square kilometers. Free space habitats. O'Neill cylinders, Stanford tori, Bernal spheres, rotating structures that give you 1G by spin, day, night by shutters, and climate by design. Aha moment, you don't terraform a whole world, you pressurize volume and paint the weather. Materials come from the moon and asteroids, basalt fibers, aluminum, glass, water from carbonaceous rocks. Each captured mid-size asteroid is a city's worth of steel and volatile. Pattern interrupt. Mass is shielding. Put slag in the walls and cosmic rays drop to background. Power is straightforward near Earth. Thin film solar at high aggregate power with concentrators and sun tracking. As you migrate outward to cooler flux, add nuclear. Fission first, fusion if achieved. Life support is closed loop. Physico-chemical scrubbers for CO2 and humidity, water distillation and membranes, bioreactors for nutrients, and compact soil-less agriculture. The trick most people miss is drift. Ecosystems wander, microbes evolve, chemistry foul. You counter with sensors everywhere, redundancy, and a culture that treats calibration like brushing your teeth. Curiosity gap. Can closed loops run centuries without resupply? Only if repair is a habit, not a hero move. Where do you build first? Cislunar space, short trips, bright sunlight, and lunar regolith close by. Park early habitats in halo orbits around Earth, moon Lagrange points for logistics. Then step to Sun, Earth L4 and L5, gravitationally quiet cul-de-sacs. As the sun brightens, habitats ride the isotherms outward. Sun, Mars, L points, asteroid belt, Jupiter Trojans. You're not tied to seasons anymore, you pick your flux. Aha moment. Migration is a knob, tune orbit, keep climate. Planets still matter as mines and labs. Mars is a school. Gravity close to Earth's rotation needs familiar day length and decent building stock in basalts. You live inside pressure shells, underground, or in buried domes. You don't bet on terraforming. You extract water ice, make propellants, smelt metals, and send feedstock up the well with nuclear electric tugs. In the outer system, Titan is a chemistry warehouse, thick nitrogen atmosphere, organics everywhere, easy aerobraking but dim sunlight. You bring reactors and get hydrocarbons free. Curiosity gap, why not stay on planets? Because planets lock you to their weather, gravity, and geology. Habitats let you set the dials. Supply chain is the real unlock. Electromagnetic mass drivers on the moon fling ore without propellant. Self-replicating factories, really recursively increasing, not literal replicators, turn regolith into trusses, mirrors, and pressure hulls. Every habitat births a workshop that builds the next habitat. Pattern interrupt, you don't launch cities, you grow them. Risk flips, debris you de-fear near Earth becomes raw material in a catcher's mitt. Radiation, water, and slag are your friends. 10 to 20 tons per square meter in the walls crush dose rates. Add storm shelters with extra water tanks and active magnetic coils for flare days. Spin for gravity, about 2 revolutions per minute at a few hundred meters radius keeps Coriolis tolerable. Test with smaller habitats first. Humans adapt if you design carefully. Aha moment, comfort is engineering, not geology. Governance is the hinge. One giant arc fails if it fails. Many independent habitats federated by trade and standards survive localized mistakes. You write maintenance into law, inspection windows, spare part minimums, software escrow, and clear end-of-life protocols for station keeping and deorbit. Curiosity gap, what's the biggest failure mode? Boredom, complacency kills complex systems. Culture is the control loop. Now stellar hopping, if the sun is a timer, choose calmer clocks. K-type dwarfs live tens of billions of years and flare less than young red dwarfs. You don't move planets, you move people and industry. First, send probes to map target systems, ice, rocks, radiation, and gas. Pre-position factory kits on icy bodies, stock power and shelter. Then migrate in convoys, habitats that are both ship and city. Target speeds don't need to graze light. 1% of sea with fusion or beamed sails puts nearby stars within lifetimes if you plan generational crews and midway refits in interstellar oases, denser clouds where you can scoop or beam. Pattern interrupt. Speed is nice. Reliability is mandatory. Propulsion choices depend on patience. Nuclear electric drives push steadily for years with high efficiency. Fusion, if practical, raises thrust and specific impulse together. Beamed light sails offload mass to the origin, large laser or microwave arrays push reflective sails outward. Curiosity gap, what if the beam fails mid-voyage? You carry backup drives and coast. Redundancy beats romance. Why start now? Because muscle memory takes time. Build small cylinders that run a decade without Earth resupply. Practice crop cycles, water budgets, waste loops, and governance. Fly a miniature shade at L1 for a week and modulate sunlight by a 10th% on demand. Rehearse an asteroid momentum trade far from anything you can dent. Aha moment. By the time you need Plan B, it's not Plan B, it's the way you already live. Final frame, Plan A buys time, Plan B buys options. Shades and nudges hold the clock, habitats and hops ignore it. The viral truth no one says out loud. The best way to save Earth's life is to move most of it off Earth. Curiosity hook, which milestone should we hit first to prove we're serious? A self-maintaining habitat for a decade or a controllable sunshade that runs all season? Will Earth be swallowed? The borderline case. This is the coin flip everyone wants answered because it feels like a final verdict. Pattern interrupt. It doesn't decide habitability, only cinematics. Curiosity gap. If the sun's mass loss pushes Earth outward, how could we still fall in? 2 forces fight, one slow and one sudden. Mass loss from the swelling sun weakens gravity, so orbits expand roughly in proportion to 1 over the remaining solar mass. That's your outward drift. But as the envelope bloats, tides crank up. Tidal dissipation inside that convective envelope saps orbital energy from anything nearby and pulls it inward. If the extended atmosphere even skims your lane, aerodynamic drag adds a brake. Aha moment. Drift pushes you out. Tides and drag pull you in. Here's the timing trap. Mass loss is steady for millions of years. It helps early. Tides stay modest until the radius gets huge. Then they spike when it matters most. Drag is 0 until contact. Then every perihelion passed through thin gas bleeds momentum. Curiosity gap, which clock runs faster at the end, outward drift or inward braking. It's a razor's edge set by envelope size, mass loss law, and how squishy the envelope is at dissipating tide. Now the kicker people miss, eccentricity. As the sun loses mass, resonances migrate and small gravitational nudges can pump Earth's eccentricity. A slightly lower perihelion during the star's biggest swell means closer sweeps, stronger tides, and a higher chance of grazing the photosphere. Those are the orbits where drag bites hardest. Pattern interrupt. Survival can hinge on a few percent in perihelion distance. Let me lay out the two endings like storyboards. Scarred survivor. Mass loss ramps early enough that Earth's semi-major axis expands beyond the sun's maximum photospheric reach. No skims, no drag capture. We end as a bone-dry, atmosphere-free rock on a wider, maybe more eccentric orbit in a dense, dusty wind. Victory condition. Not eaten, not habitable. Grazed and doomed. Envelope growth and late-stage tidal dissipation win. Earth's path intersects the puffed atmosphere. Even a skim through tenuous gas robs orbital energy each pass. The orbit shrinks, tidal heating rises, drag strengthens, and the spiral accelerates. This isn't a single plunge, it's orbits to orbits, quick on geological clocks, slow on human eyes. Aha moment. Once you touch gas, the game tilts downhill fast. Common mistakes to avoid. Treating mass loss as a guaranteed rescue. Helpful early, not decisive late if tides spike. Assuming engulfment means instant vaporization, ablation is fast, orbital decay takes multiple passes. Believing a cooler red star is gentle, total luminosity is huge and spectrum shifts toward near-infrared that heats efficiently, even if there's nothing left to heat. Forgetting dust. Local dust shades a little, but re-radiates in infrared, warming surfaces that absorb IR well. What would the tells be to a distant watcher? The sun's angular size swells, color reddens, and total brightness at Earth's shifting orbit still climbs. Perihelion seasons glow hotter than aphelion by an increasing margin. Eccentricity is up. Spectra reveal a thick, dusty wind, and later, if we're doomed, subtle orbital period shortening between close passes. Could engineering help at this late stage? Shades can't cancel orders of magnitude luminosity jumps. Orbit nudging is too slow to outrun tidal spikes on million-year ramps. The only assist is the sun's own mass loss pushing outward, and that's not a plan, it's a coin toss. Pattern interrupt. The headline is theater. The deadlines were upstream when the stratosphere turned wet and the biosphere lost its CO2. If you remember one line, make it this. Whether Earth is swallowed or spared, habitability ended earlier. The final flip decides the spectacle, not the outcome. Here's the takeaway. Earth loses habitability quietly. Moist greenhouse, CO2 starvation, and ocean loss. Long before red giant theatrics settle the swallow or spare coin flip. Want the practical plan? How much shade buys how many years? Which asteroid cadence safely grows our orbit? And the first off-world habitats to build? Watch the next episode where we rank mirrors, momentum, and moving house by years saved per kilogram. Subscribe so you don't miss the engineering chapter.